In this video, we're going to learn about molecular geometry and VSEPR, or VESPR theory. VESPR theory states that electron-electron repulsions will result in a maximization of the distance between electron domains in a molecule. So, for example, if we have carbon dioxide, the bonding electrons between the carbon and one oxygen and the bonding electrons between the carbon and the other oxygen are going to repel each other, and they're going to be as far apart as possible, in this case giving us a 180-degree bond angle. It's not going to be something like, say, this, where you have a lot of space on this side and very little on this side because there's such repulsion between the electrons here and here. This doesn't make any sense, but this does. So it's worth noting, I mentioned electron domain. This is defined as a region in which bonding or non-bonding electrons are likely to be found. And the number of electron domains is sometimes called the steric number. Another thing worth noting is that it doesn't matter whether you have a single, double, or triple bond, all of these constitute one electron domain. So let's do some analysis here. Two electron domains. We have, say, carbon dioxide, and we have hydrogen cyanide. And in both of these cases, you can see that there are just the two electron domains. These are linear. I have a central atom, and on the one side of the carbon, there's an oxygen. On the other side, there's an oxygen, and that's it. And these two sets of bonding electrons repel each other so that they are as far apart as possible. And also over here with the HCN, my hydrogen, my carbon, my nitrogen, and the nitrogen also has a lone pair. Notice how the carbon has two electron domains, and they are as far apart as possible. The bonding electrons between C and H and the bonding electrons between C and N. Also, the nitrogen has two electron domains, being the lone pair here and the bonding electrons between the C and the N. And the final thing that I do want to note about these is that it doesn't matter whether we're talking about a single bond or a triple bond or a double bond, they all count as one electron domain, and they all have the same effect of repelling as one another. So that is all on the two electron domain substances. How about if there are three electron domains? Well, we're going to go with BH3, and we're going to go with CH2O, and we're going to go with NClO. All right, here they are. Now, in the previous case, you saw in the example the 180-degree bond angle, but here, these are definitely not 180-degree angles as I move these into place. These are not 180-degree bond angles. These, well, the first thing you might notice about them is they are all flat. They all look to be two-dimensional. And so if you were to say that going all the way around them is 360 degrees, and you were to break that into three equal parts, then you would get a 120-degree bond angle. So I'm actually going to write that in here. This is 120 degrees, and the same thing could be said in the CH2O. Note how it doesn't matter if we're talking about a single or a double or a triple bond. If there is an atom where there is bonding, that just counts as one electron domain. And so this is 120 degrees. Now, when we get over to the NOCl, this is a little bit interesting because what we can say is that the the lone pair on the nitrogen pushes a little bit harder than the bonding pairs. And so the bond angle between the chlorine, nitrogen, and oxygen, it's going to be near 120 degrees, but we're going to say it's a little bit less than 120 degrees because this lone pair is pushing here and it's pushing here. It just causes the Cl and the O to be a little bit closer together than otherwise. It's about 117 degrees, but you don't have to memorize it. Let's say it's less than 120. Next, we have where there are four electron domains. So I will replace these and go to there being four. Now, what might be first striking about this is that on the screen you can see these all look flat. They all look two-dimensional. Well, quite clearly, this is a three-dimensional structure. And so although this looks flat here on the screen, and it looks like, oh, if there are 360 degrees around, then each angle should be about 90, 90 here, 90 here, 90 here, and 90 here. It's not the case. Just looking hydrogen to carbon to hydrogen, that is evidently, it looks bigger than a right angle. It looks bigger than 90 degrees. And in truth, it is. This is actually about 109.5 degrees. And that's something that some geometry would get you to. Some 3D geometry would get you to that. But you can just memorize it as 109.5 degrees. In the case of the NH3, it also has 4 electron domains, one sticking up here, the lone pair, and then the 3 hydrogens at the base. But because there's a lone pair, we're going to say that the angle is a little bit less than 109.5 degrees. In the case of H2O, there are 2 lone pairs here and here, and then the 2 bonding electron pairs. And so because there are 2 lone pairs, the angle is going to be even smaller. We'll just say less than 109.5 degrees. In truth, this is around 105. This is around 107, and this is around 100. This is exactly 109.5. Finally, in the case of HF, we're going to say that the fluorine does have 1, 2, 3, 4 electron domains, but you can't really talk about a bond angle since there are only 2 points here. There's only the hydrogen and the fluorine and not a third atom. There's no vertex for an angle with 3 points. So we'll just ignore the concept of bond angles there. But I do want to point out that the fluorine does have 4 electron domains around it. All right, so next we're going to talk about the names of geometries. And these names are divided into categories of electron pair geometry and molecular geometry. The electron pair geometry simply is based on the number of electron domains, whereas the molecular geometry is based on the number of bonding and non-bonding domains. Let's put this into practice. We'll refer often to this chart to understand it, but for now, okay, let's go back to these 2 electron domain containing compounds, the CO2 and the HCN. Both of these have the same geometry in every way. Around the carbon, we're going to say the carbon and the CO2, it has an electron pair geometry and a molecular geometry that are known as linear. And you can say the same thing about the carbon in the HCN. And the way that we look at that is you go to that central atom and you see that there are 2 electron domains, one here for the carbon dioxide. Again, you can say the same thing for the carbon here. There's 1 and 1, so there's 2. So in the case of there being 2 electron dense areas, we can say that the electron pair geometry is linear, and there aren't any lone pairs, so the molecular geometry is also linear. Moving on, when there are 3 electron domains, let's talk about CH2O and NOCl, which I'll flip like this. So the molecular geometry, if there are 3 electron domains, the electron pair geometry is known as trigonal planar. And we can count the electron domains here. There's 1, 2, 3 in both cases, 1, 2, and 3. And so the electron pair geometry is known as trigonal planar in both cases. And you can get that straight from, I'll go here. I'll get that straight from here. When we have 3 electron dense areas, the electron pair geometry is always trigonal planar. Now, in the case of the CH2O on the left, there are no lone pairs, so the electron pair geometry is the same as the molecular geometry. I'm in the molecular geometry area here. Trigonal planar is the case for our CH2O. However, in the case of the NOCl here, yes, it may have a steric number of 3. it may have an electron pair geometry that is trigonal planar, but because the molecular geometry, because it has one lone pair, the molecular geometry is known as bent. And if you look at this angle here, if we kind of ignore the lone pair, this looks like a bent shape. That's the reason for the naming as it is. So that's why we have both cases electron pair geometry is trigonal planar, but the molecular geometry for the CH2O is trigonal planar, whereas the molecular geometry for the NOCl is called bent. Moving on. We have 4 electron domains. So if there are 4 electron domains, we would say that the electron pair geometry for all 4 of these is the same. It is tetrahedral. It is tetrahedral, and we will go straight to that chart again, and we can see if there are 4 electron dense areas, the steric number is 4. Always the electron pair geometry is tetrahedral. Tetrahedral, 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 and tetrahedral. But if we're talking about molecular geometry, that's when we can get some differentiation. In the case of the CH4 has no lone pairs around that carbon, so its molecular geometry is the same as the electron pair geometry. It is tetrahedral, as we see here. So that's our CH4. But if there's one lone pair, as in the case of NH3, which we're looking at here, there's one lone pair, well, it is trigonal pyramidal. And we see that by looking at this chart. We have steric number of 4 with one lone pair. NH3 is trigonal pyramidal. Next, if we have 2 lone pairs, as in the case of H2O, right here, it is bent in terms of its molecular geometry. And we get that by looking at this chart, 4 electron dense areas with 2 lone pairs, a bent geometry. Finally, yes, it's possible to have a case of there just being the no bond angle and the 2 atoms. Look, if there are 2 atoms, just call it linear. And that's the case with the HF, where there's only the fluorine bonded to the hydrogen with no other bonds. We're going to call this a linear structure. So that is molecular geometry and VSEPR theory. Hope this video has helped. Feel free to leave any questions or comments in the comment section below. Thanks for watching.